this was the definition before. And now we can test this definition, and I think we saw this like something like R epsilon on the epsilon squared. This is non-reduced, and well, we can also think of more interesting schemes like this one, x y squared, which looks like this. Well, first of all, I have this coordinate cross, and then I have y squared equals 0. So it's like an embedded little vector here, and this is non-reduced. Classically, it's also non-reduced in our sense here because I have the global function y whose square is 0, but yeah, and this is not the case. Okay, so this is also non-reduced, but I mean, this works because we have lots of global functions, and if we don't have many global functions, then this definition becomes more or less empty. And so the counter example we had is just we take P2 and let's call the homogeneous coordinates x, y, and z. And now let's take as a subvariety of W the vanishing set of x squared, which looks like a double line. So like a pad line, pad P1 in P2, and we don't want this to be reduced. Yeah, but when we did the calculation, and as I mean, at some point we calculated the functions on P1 that they're only constantly many, so only the constants, and well, it's the same here. So let's count this down into R, just R. And so we have no, so this is more or less empty, because I mean the only nilpotents are those we already have in R. And well, the idea to calculate this is that so this P2 is covered by the standard affine charts where x is non-zero, y and z are non-zero. Then this W is covered by uy and uz, because well, when x is this ux has no intersection with this, because x is here, it is invertible, and yeah, it's not. And okay, and now so whenever we have some map here, then on the chart we can write f as some homogeneous polynomial in y and z over y to n. So this is homogeneous of degree n. And on the other map we have h, x, y, z over z to the m. Also, this is homogeneous of degree m, and in both affine charts we have x squared being 0.
The notation you have to G.
Sorry, this is the same m. Yeah, so this is on u y on uz, but on the intersection of these two, they have to coincide, and then you get some equation like to the n h equals y to the n g, and z is regular, so this has to divide g m times, and so sorry, this is g This is h, so that has to divide h m times. So we would have replaced this h by something where there's no z in the denominator, and then it has to be equally 0, so which is the constant. Yeah, so I mean this should be the same proof I think we have for P1. I mean, it's important that I have. I mean, it does not work just with all that here, because I need the second chart, in which something happens so that I can compare. Okay, so this does not work, this naive definition, because then the schemes become reduced only because they do not have many functions. And then Hugo proposed different definition for reducedness, namely instead of I mean every such function defines some closed subset, so we can just start with closed subsets and ask so for all the x closed. Now we take the equations of the x, so pointwise equation. But we can say something like the nth power of these is everything, and then we can ask whether I'm following this. So this is better definition. So substitute the earlier one. And for this example, for this P2, or this W here, we can now use the as closed subsets. We just take the one spanned by x, because now the square is clearly 0. So we have this for n equals 0, but it's not the case that this here, which is just an ordinary P1, is the same as our best P1. So here we see that we get this better definition. We get rid of the projective problem here, but it still relies on the fact that on a projective space we have lots of closed subsets. And now for more general spaces, it's now it's a bit unclear how to proceed, but just so what we want are maybe, I mean, for a good notion, good notion of reduced should have fulfill the following extents. So one is whenever x is reduced and u and x is open, then u is reduced as well. So open subscheme should inherit it. And second property, x is covered by reduced. Yeah, so that is time, so it's covered by reduced opens. Then x should be reduced as well. And now let's try to prove the things. So x will be 2. With this better definition, so we take so when we have v and x is closed, then we can just, and we know that v to the n is everything, and v intersected with ui is closed in ui. Still have that this is everything. UI. Now I reduce this of the UI. We know that not V capital I is Y, and this is the same as not V I is in V. But this is the case for all UI, from which we can conclude about that next. Union for all UI, we have that it's not the case that X is in V. Okay, so, and this, I mean, we can prove this because we can restrict closed propositions to open subspace. But in order to prove axiom 1, we would start with something which is closed in an open, and it's unclear how to extend closed proposition to the whole of X. And it's, I think, yeah, we cannot, I think one can show that one cannot show such a extension exists. But we can at least, so this is unclear how to proceed here, and yeah, I mean, it's related to the fact that, I mean, so I just said any X here, not non-projective, it's unclear what the closed subsets, I mean, how many I do have. But it works. Axiom 1, so let's call it the, so just axiom 1/2. So if X is just affine, and union X is, so now I have to say basis open, basic open. So that's df. Then axiom 1 holds. So X reduced implies df reduced, and well, I mean, now I take some closed subset of df, which is, so say some V, which is given by some equation. Well, this equation is an equation, it's given by a global section, so a global function on X, and maybe with some F's in the denominator. But I can replace, I mean, you can just remove F to the N here. Because it doesn't change anything on the F. And then I see that V is induced by a closed subset on X. And then I can, yeah, then I can use the reducedness of X to show that, yeah, this is reduced. Okay, but this now, so we just have this, but this now would allow us to define it by hand. It's not very pretty. This was just the upshot of the discussion to say that so if X is a scheme, then X reduced by definition if there exists a cover by affines, affine open, such that UI is reduced. And for an affine scheme, I can just use the better definition of the naive definition. Because now this definition clearly fulfills axiom 2, but it also now fulfills axiom 1. Because when I have, because I mean, from axiom 2 and axiom 1/2, it follows that any open in an affine is reduced if the affine is reduced. Because any open in affine is covered by basic opens, and these are reduced, and by axiom 2, the union is again reduced. And so this means also that instead of just taking any, so I can also say that for all covers. Let's say this. the same holes. So I can check any cover and then what covers. And when X is a general type, then we may not have any interesting open cover. So it's unclear. And then of course then also this is unclear to choose. We can be a bit more general by allowing not only open Zariski open covers, but for example Ital open covers, because this should also reflect reducedness. And then you have a bit more types. I mean things that are covered, that have an Ital cover. So yeah, so maybe you can define what an algebraic space is by saying we have an Ital cover them, yeah. And then yeah, so then we have a bit more general, but it's still not yeah. I mean this is much nicer, although it seems to be not the wrong notion, but at least because this works for any type. Yeah, but I think any good notion of reducement should be in Zariski local. No. And maybe so I don't know how so maybe one of you has an idea. Maybe we can also measure non-reducedness point-wise. I mean, if one thinks of this example, I mean, it's reduced everywhere except at this point. And let's we go back here to this example. If we calculate the Kähler differentials here, then they are generated by d epsilon, and the relation is 2 epsilon d epsilon is 0, just by differentiating epsilon squared. So I mean, this is topologically, this is just 0-dimensional. Yet I have a non-trivial differential form. So I can just take at the cotangent module, and I mean at least Kletzler would, and see okay it jumps here, and then I see it's non-reduced. But yeah, it's a question how to maybe so do we find something which matters point-wise non-reducedness? And the problem is here maybe it's unclear what the topological dimension is. I mean, we can define the dimension by taking the rank of the cotangent sheaf, but then we are missing a second version of defining the dimension and see whether we have a jump here. Yeah, but so yeah, okay, so maybe this, I think this is all we discussed. Yeah.
Makes sense for this area presentation. We have an intuition, or anyone, if we should expect that we have an operation which reduces a scheme. So it seems to me to be unlikely in reality, but I mean, usually in algebraic geometry, it's something we have which is useful.
But you divide out too much. I mean,
yeah, I mean, you can't use the reduction on algebra side, but
yeah.
I mean, examples we have seen, we know what the reduction should be at this point for the x square example in P2, it should be P1.
If you have like a curve analysis of because reduction is it's the wrong way we can't do this in cohesive stuff because it's
yeah, I mean it's also something that makes it unlikely. Yeah,
and I mean being reduced is not a property of fibers. Because as soon as we take we have something reduced, as soon as we take the fiber over something non-reduced,
yeah,
it carries over.
So the reduced types are not closed under pullbacks. This is something one should keep in mind.
Yes, yeah.
Because pullbacks are intersections, and when I intersect a circle with a tangent, then I get medicinal lines and move that again.
Yeah, and this is also, I mean, all of these definitions, I mean, they say something that all non-reducedness comes from the base.
you want to think of the map from the circle into the plane as a reduced morphism. So morphism of reduce instead of reduce.
I mean, now I was just thinking the domain and codomain are reduced.
Yeah.
So we have the tangent, we have a diagram in the types. Yeah, so what I said was, I guess, different from what Marc was.
No, I think it's but it's, I mean, when you, so you have a circle, and this is reduced. The circle is over the line, and now we take some. Maybe the simple example is just R epsilon over epsilon squared. It's just fiber of R.
Mm-hmm.
Maybe over itself. So.
Mm-hmm. Yeah.
And you can draw a circle around if you want.
Yeah.
So I would expect for point-wise characterization, probably you should look at every point you have an infinitesimal disk, or the whole monad, so everything that's not included. This, the functions on this are like stock or structure sheet. It's a inverse limit. It's a bit more than the point, it's also the infinitesimal limit. I would expect you can characterize reducedness on these.
Okay, so you mean instead of taking our affine cover, we take pointwise.
Yeah.
Cover sizes.
Yeah.
I mean, basically, you have this theorem where that scheme is reduced at every point. The stock of this sheet is reduced.
Yes, but I mean this is roughly axiom 1 and 2.
Yeah.
But when we go pointwise, we have a problem that, I mean, R epsilon over epsilon squared is also point in R.
Yeah, but they have different infinitesimal. They have different models, so all the points of R are not equal to 0. That's not the same as the one around.
Okay.
And you want.
So if I take the formal disk of a point in this infinitesimal line segment, I get the infinitesimal line segment. And if I take the formal disk around the point in A1, I get like something really big
But what is the point in A?
on a small scale. Yeah, so maybe there's a way to say we have like a formal disk that is big enough, and then it's reduced, and if it's too small, it's unreduced. I'm not sure. But it's
No, and here it should actually be larger, not smaller, because I mean you have the directions of R and the epsilon.
yeah, I'm not sure if you kind of, when you quantify over all points, you kind of also see the not really existing points in your small line segments move outward. Yeah, but okay, so we'll point to. I guess we have a candidate now.